All right, so we're going to start a new lesson, Chapter 5, Section 1. This is a very long section, so I'm going to split it in 3 parts. So today, in this lesson, I'm just going to be going over the graphs of exponential functions. In 5.1b, I'm going to go over some equations, and then in 5.1c, I'm going to go over some real-world applications and compound interest. This first part, maybe you've seen before in Algebra 1, depending on what that experience was like. If you were in honors, chances are you have at least done a little bit of exponential functions. Maybe you've been introduced to them before, but maybe you didn't go into a lot of depth with graphing them. This lesson, just this first part of it, is just going to be graphing exponential functions. All right, so an exponential function with base a has this notation, f of x equals a to the power of x, where a is greater than 0 and a doesn't equal 1. First, note that this is different from things that we've done before. So keep in mind, a is supposed to be a number, right? Sometimes you also see the letter b, and that's actually a little bit more typical. Like sometimes you'll see f of x is b to the power of x. Right, b meaning base, right? So b, I'll just say b means base. Now, an example of an exponential function might look something like f of x is 2 to the power of x. Notice that your variable is in the exponent, right? In all the functions that we've done before, we haven't seen the input of a function be in the exponent. So hopefully you can see that f of x is 2 to the power of x is different from, say, g of x is x squared, right? Notice that your variable here is a base. It's not the exponent itself. Even though you see an exponent, right? 2 is an exponent, but it's not an exponential function, right? Here, our exponent is the variable, right? So that's what makes this an exponential function. So there's 2 main types of exponential functions. There's a growth and a decay. We'll talk about that in the next slide. But first, I want to talk about this restriction right here. A cannot equal 1. All right, so think about that. Think about why it cannot equal 1. All right, well, why don't we write a function? I'm going to say f of x is 1 to the power of x, right? So this is when a is 1, and let's see what happens there. Well, hopefully we know from way back that 1 to any power is going to get you 1, right? So let's say I had f of 0, right? Anything to the 0 is 1. F of 1, right? 1 to the 1 is 1. F of 2, right? 1 to the 2 is 1, right? 1 times 1 is 1. And you could keep doing this forever and ever, and you're going to get 1 every single time, right? So that's why our base cannot be 1, because we're just going to keep getting a 1 from our output, right? No matter what exponent you put there. Right, so what makes an exponential function is if the base is anything that's not 1. All right, so it does need to be greater than 0, right? If it's not greater than 0, so like if your base is a negative number, then some strange things happen, and we're not going to get into that. But something does happen whether it's greater than 1 or less than 1, and we'll talk about that in the next slide. All right, so this is visually what an exponential function looks like, and this is the distinction that I was making in the previous slide. All right, so you can see in this first example here where f of x is b to the power of x, where b is greater than 1, you can see that it looks like it's shooting straight up. See, from left to right, it's going up. And the next one, f of x is b to the power of x, we see that 0 is less than b is less than 1, so basically b is a number, just any number between 0 and 1. We see that it's going to start really, really high, and then as x gets bigger, it goes down, right? So it's decreasing, right? So this first one right here, this is going to be an increasing function, and we call this exponential growth, right? So if you hear me saying this is a growth function, right? That's what this is, an exponential growth, right? And you can see here in this next one that this function is decreasing, right? So it's going down from left to right, and we typically call this exponential decay. All right. Now, in real world applications, you maybe hear words like I don't know if something represents an exponential decay, like depreciate, or something might lose its value. For an exponential growth function, you might hear that the value of something appreciates or inflates, right? So when you hear about inflation, when people talk about money, typically those represent an exponential growth function, right? So this is probably, and you'll see later on in this same lesson, you'll see that there's some real world applications with exponential functions in terms of money. But one thing to note about these functions is the graphs are going to basically take the same shape almost every time, right? So this exponential growth function, we can see that it's going to cross the y-axis at 0, comma 1, right? So it's always going to be true if we have just something with a base and the exponent, right? Nothing more. So you see a b to the x, nothing more, right? And this is almost always going to be true, right? So you want to kind of make a table. So use a t-chart to graph. That's going to help you guys. But it's also helpful to know some basic points every time, right? So if you have something that is just a basic exponential function, and you know that it's going to be an increasing, you know that the b value is greater than 1, we're always going to want to graph 0, comma 1 first. And then right after that, we're going to do 1, comma b, right? And sometimes that's all we need to graph our functions, but sometimes we want to go at it a little bit more, right? So sometimes we want to see what happens at 2, right? And then we want to graph maybe 2 and something else, right? Another number that we get from making a table. Or sometimes we want to go backwards. Sometimes you want to pick a point right here and pick, I don't know, -1, comma another number, right? Whatever we get when we make a table. Same thing with an exponential decay function. We're always going to start at 0, comma 1. And then since it is a decay, we know that 1, comma b, our base is gonna go below 0, comma 1. And then again, if you want some more values, just make a table, pick some points, right? There's some other points that you could use. The domain of an exponential function is always going to be all real numbers. And it's kind of hard to see from these images here, but if you extend this line, this arrow going this way forever and ever, you see that it kind of hugs the x-axis, right? It's never going to touch it or cross it. This gives us something that we call an asymptote. Right, and I'll give you a quick little vocab word. An asymptote is a line, right, that a curve approaches but never touches. Right, so it's a good thing to know. I believe in these examples, I'm not going to ask you what is the asymptote of the function, but it's good to know that it's there because it'll help you with graphing, especially later on in this same lesson when we get to the transformations. So when we shift it up and down, it's helpful to know where we want to kind of approach, right? You're not just going to decrease or increase from wherever, right? You see that here we're going to kind of hug the x-axis, and then this is our asymptote right here, this imaginary line that we approach but never touch, right? So same thing over here in an exponential decay. As you go to the right, you see that we're going to approach the x-axis. We're kind of hugging the x-axis a little bit if you drag this curve out a little bit more. And we see that we're approaching it, and we can get really, really close to the x-axis, but we're never going to touch it, right? So that is our asymptote of this function. All right, so I know I said a lot of information so far, but we're going to practice graphing in the next few examples, and then hopefully you see that it's not super difficult. All right, so here are 2 examples. These are maybe some of the most basic examples that you're going to see. in terms of exponential functions. Now, the strategy with graphing these, there's two ways that you could approach it, right? The first way is to know the two basic points and then maybe pick another one if you need. And so the first way to do it is to always plot 0, 1 and 1, b, right? Each and every single time. Know that b is your base, right? So I'm going to look at number 1 here. What is our base of this function? Well, we have a 2 to the power of x. Anything that has the exponent is our base. So I'm going to say b equals 2, right? That is our base here. So we can just simply graph, right? I know that's going to have a point at 0, 1 and 1, b, but in this case, b is 2. So 0, 1 and 1, 2, I'm going to plot those points. I have one right here, and then I have 1, 2 right here. And we know that the general shape of an exponential function is going to start really, really small, and then we're going to shoot straight up. So I know it's going to look something like that. And then because I know that an exponential function has an asymptote, meaning that we're going to approach this line but never touch it on the x-axis, then I know that I can't dip below, right? So you don't want to go like that, right? That would be incorrect because we're never going to go below the x-axis. We're just going to approach it but never touch it. All right, so this is the general graph. The other way that you could do it, if you don't want to commit that to memory, right, make a table, right? So make an f of x table and plug in some values. I like to pick -1, 0, 1. You don't need that many because the shape of these functions are very predictable, right? And then you're going to see that as we go along, right? But when x is -1, f of x is going to be 2 to the -1. And then if you remember, negative exponents bring it to the denominator or flip it, right? So it's going to be 1 over 2 to the first power, which is just 1/2, right? So then we get a point at -1, 1/2, which is about right there. All right, and then when x is 0, we get 2 to the power of 0, and anything to the 0 is 1, right? So 0, 1, that's where that point comes from, and that's why you can see that it's almost always going to be the case. It is always going to be the case when it's as simple of a function as this, right? With the transformations, it might change it around, but for now, that's what you need to know. And then for x equals 1, we get 2 to the first power, which is just 2, which is our base, right? So that's where that 1, b comes from, right? So 1, b is going to get you something like this, and then we still have that same shape that we originally graphed, right? So it's up to you. If you like working out the table and you feel it's more accurate that way, do it that way. Or you can just know 0, 1, 1, b, and then if you need more points, pick another point, right? So pick another value of x to plug in if you need. All right, so let's do the same thing with the next example, number 2. Again, you can do 0, 1, 1, b, and then plot those points. 0, 1, we know that that goes right there. And b in this case is 3, right? That's what we have raised to an exponent, right? So we have 3 to the power of x. That means it's going to be 1, 3 as our ordered pair, and that's going to end up right there. All right. Or make a table, right? So if you make a table, again, I like to pick -1, 0, 1. And then again, we have 3 to the -1, which is 1/3, right? 3 to the 0, which is 1, and 3 to the 1, which is 3, right? So we end up at these same points, but then we just have another one that goes down here. And then just like before, know that we're going to hug the x-axis a little bit, never approach it, and then you can see that we're going to shoot up, right? So always, 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 they're going to have the shape that looks something like that, or if it's a decay, it's going to look something like that, right? So it's always good to know. The shape of these are very predictable. All right, let's keep going. So we know that in example number 3, 10 is our base, right? So we can just pick 2 points. We know that 0, 1 is going to be a point, and 1, our base is going to be another point. In this case, our base is 10, so 1, 10. So I'm going to go ahead and plot these points. I have a 0, 1 right here. and then a 1 comma 10. All right, that's going to end up way up here. Right, so, and that's actually enough information, right? We know that it's going to start really, really small. So we know that we need to hug the x-axis, right? Remember that this is what we call an asymptote. It's going to approach but never touch the x-axis. And then we know it's going to shoot straight up, right? So as you can see, the shapes, like I said, are very predictable. We should know what it's going to look like. It's just a matter of how quickly it's going to go up. Right, because some of them, as you can see in this one, since there was a bigger base, it gets larger very quickly, right, as opposed to the previous two examples, right? So we get something like this. And again, if you're somebody that makes a table, you can make an f of x table. Again, don't pick too many values because we know what the shape of it's going to look like. -1, 0, and 1 are fine. And then we get, with -1, 10 to the -1, which is going to be 1 over 10, right? Remember the negative flips the fraction. 10 to the 0, which is 1, and 10 to the 1, which is 10, right? And then you see that we get these same 2 points that we had originally started with. Just we get a 1/10 right there, which you can see that it starts really, really, really small. Right, so that's maybe if you want it to be a little bit more accurate, but it's fine. This is enough information. All right, number 4 is where it starts to get a little bit different. Right, notice that your base now is 1/2. Right, typically we've only done numbers, I mean, at least in these first 3 examples, we've only done numbers or bases that are bigger than 1. Remember, there's 2 main types of exponential functions. There's a growth and a decay. And in a growth, your base is bigger than 1. But in a decay, right, your base is between 0 and 1. Right, so in a decay, we have our base is between 0 and 1. And in this case, our base of 1/2, right, 1/2 is between 0 and 1. Right, so we know that this shape is going to look something like that. That's our general shape. All right, it's going to start really high, and then we're going to decrease, and then it's going to get really, really low and kind of hug the x-axis. All right, so we can still do the same thing, right? We can still say 0, 1, 1, b. Just in this case, b is 1/2, right? So we know that we're kind of going to go down a bit, right? So in this case, 1, b, let me write that down, is going to be 1, 1/2. So I'm going to write this down. 0, 1, I know is going to go right there. 1, 1/2 is going to go somewhere right there. This really is enough. I know that I can just kind of draw the line, the curve going in this direction, right? Making sure not to cross the x-axis. If you want to make sure that you're going high, an appropriate amount of units, right? So something like that, then you can maybe pick another point. Right, so if it's not clear what the shape of it's going to be, I would definitely pick some values just to see what that's going to get you, right? So I know that some values that I like to pick, again, are always going to be -1, 0, and 1. So we have an f of x over here. I'm going to pick -1, 0, 1. And for -1, I know that I have a 1/2 to the negative first power. Remember, the -1 is going to flip the exponent. I mean, I'm sorry, not flip it's going to flip the fraction, right? So it's going to become now 2 over 1, which is just 2 to the first power, and 2 to the first power is just 2. So that's going to get us our extra point, right, at -1, 2, right there. And then we can see that we're going to kind of now go up a little bit more. If you want to pick another point going backwards, you can. Right, so I'll just fill in the rest of this. I know that 1/2 to the 0 is going to get you 1, right? Anything to the 0 is 1. And then 1/2 to the first is going to get you 1/2. All right, but if you want to kind of go backwards, like let's say you want to go, maybe this isn't clear enough. Maybe you want to go backwards and do -2, or I'll write it down here, right? If I wanted to do -2, then I would get a 1/2 to the -2. And then again, that negative exponent is going to flip the fraction. 1/2, the reciprocal of 1/2 is just going to get us a +2. We get a 2 to the second power, which is 4. And then you can see that now at 2, we have an even clearer picture of what this graph is going to look like. So again, I know that it's going to hug the x-axis as x gets bigger. And then as we go in the negative direction, I know that we're going to go up. Right, so that's the difference between these kinds of functions. But again, like I said, the shape is very predictable. I know that it's either going to start really high and then get really low, or it's going to start really low and then get really high. And that just depends on what our base is. All right, so notice in these two examples also, right, our base here is a number that is between 0 and 1, right? 1/4 is less than 1, but it's bigger than 0. So I know that this is going to be a decay. I know it's going to look something like that. And then same thing with number 6, right? 1/10 is less than 1, right? But it's bigger than 0, so I know it's also going to look something like that, right? It's going to be this decay function that's going to start really high and then it's going to get really low. All right, and then to find values that you want to plot on your graph, again, you can do 0, 1, and then 1, b. In this case, it's 1, 1/4. And then you end up with a point right there and then a point right there. To get something a little bit more accurate, though, you might want to do a table, right? So maybe you want to do an x f of x table, and then you want to include -1, for example. And then at -1, I know that 1/4 to the negative first power, the negative exponent is going to flip it, so we get a positive 4 to the first power, and that's just 4, right? So -1, 4 is another point that we can plot on our graph, and then it's going to look something like that. And then you can see that when you connect all these points, we're going to start really, really high, and then we're going to kind of hug the x-axis a little bit, not crossing it. I know that when I drew it just now, it is kind of crossing it a little bit, but that's fine, right? As long as you can see that it's really, really close to it. All right, same thing with number 6, right? So again, you can draw an x f of x table and do -1, 0, and 1, right? And so -1 is going to get you 1/10 to the negative first power. Again, that's going to flip your exponent. Flip your fraction. You get 10 to the first power, which is just 10. And so we get a point at -1, 10, which is way up here. So again, even though they all have the same shape, right, this one starts really, really high and then gets slow faster, right? So then 0, 1/10 to the 0 power is going to get you 1. And then 1/10 to the first power is going to get you 1/10, right? So that gets us our other 2 points. And then we can just connect them. We can see that it starts really, really high, and then we're going to get really low. All right, and then our graph is going to look something like that. All right, so here we have some slightly different examples. Now we see that our exponent, right, if you noticed in all of the other examples, our exponent was just an x, right? And in number 8, we didn't have a negative in front of whatever our base was, right? So maybe you might want to make a table, right, an x f of x table, just to see what's going to happen, right? So if I have x and f of x here, I might still want to pick the same few values, right? So maybe I want to pick -1, 0, and 1, and see what that does to my function, all right? And so if x is -1, we get 2 to the -1, right? Remember that negative is already there. There's already a negative there, and x itself is -1. So we get -1, which is going to be a +1, and then we get a +2. So when x is -1, we get a +2. And I'm going to plot that point right there. All right, and we can do the same thing with 0. We get 2 to the -0, right? -0 is just 0. So we get 2 to the 0, and anything to the 0 is 1. So we still get that 0, 1 that we've observed in the other examples. And then for x is 1, we get 2 to the -1, right? And then negative exponents we want to flip. So we get 1 over 2 to the first power, which is just 1/2. And then we get that point right there. Right, so we can see that it originally looked like it was going to be an exponential growth function, right? Because our base is bigger than 1, so we would expect it to look something like that. But when we connect the dots, we can see that it's actually going to be a decay function, an exponential decay. So it's actually going to look like this and not like that, right? And one way to think about it is remember that a negative exponent, let me erase this right here. Remember that a negative exponent flips the base, right? So this is now going to become 1 over 2 to the positive x, right? And now that looks a little bit more like a decay function, right? Or another way that you could do it is you could say if 2 is raised to the negative x, then flip the 2 is going to be 1/2, but still raise it to the x power, right? So now this looks definitely more like what we've seen before with a decay function. All right, so again, if you're ever confused, if you're ever not sure what to do, make a table, right? You don't need that many values. You just need a couple just to get an idea of what the shape is going to be. All right, let's try the same thing with number 8, right? I don't know what that negative is going to do, right? Let's say we had no idea what it's going to do. If you remember from a little while ago, our topic on transformation of functions, maybe you have some idea of what it's going to do, right? But again, pick some values and test it, right? So I'm going to pick x, f of x, and then as always, I'm going to pick -1, 0, and 1, right? We don't need that many. And then so we get -3 to the -1. Hopefully you remember, right, from maybe like the first week of school, right, our topic on exponents. If you don't see the negative in parentheses with your base, so for example, if you don't see this, then you're not raising the whole thing to that exponent, right? It's just going to be whatever this is right here, right? So let me go ahead and erase. All right, let me go ahead and erase this, right? Because it's just our 3, right? It's just the 3 that's going to be raised to that exponent, right? So then -3 to the -1 is going to get you -1 over 3 to the first, right? Remember, this negative exponent is going to flip your base, and then this negative out front is just going to make it negative. So then we get -1/3. I'm going to plot that point. -1, -1/3 is going to be right there. All right, let's do the same thing with 0. I have a -3 to the 0. Remember, it's not -3, the entire thing that's raised to the 0. It's just the 3, and your answer is negative. So we get a -3 to the 0 is 1, right? So 0, -1 is going to be our next point, right? Let's do the same thing with 1. We get -3 to the 1, and then remember, it's not -3. That's all raised to the first. It's just the 3, and then your answer is negative. So we get a -3, right? Either way, in this case, it would work out the same. But let's say I picked a 2, and then let's say you got this messed up with a 2. Then you would get -3 to the second power. If you squared -3, you would get a +9, right? Hopefully we see that we are not squaring -3, we are squaring just a +3, and then making our answer negative. So that gets us a -9, right? So please don't get that mixed up. But I'm going to plot the points that we have. So we have a 1, 3, and then a 9 is going to be down here, right? And then we see that we're kind of still hugging the x-axis and getting bigger, but we're getting bigger in the negative direction, right? So our function is going to look something like this. And then that's what this negative out front is going to do. This negative is going to reflect over the x-axis. And then in our next slide, we're going to talk about transformations of exponential functions. They're very similar to the transformations that we've done way back, but you'll see what it does to our function itself. And then hopefully you can see in this example 8, it looks like the normal function that we've usually done. It's just the whole thing is flipped over. All right, and we'll talk more about that in the next slide. All right, so our transformations are going to work as follows. I know there's a lot of information on this slide, but I'm going to go one by one. I'm going to show you what everything means. And hopefully you're going to see that we've done something similar before, just not with exponential functions. All right, so vertical and horizontal translations. So we call those shifts when I taught it before, I think in chapter 2.5. Translation, shift, right, or that's how you guys know it, shift. Vertical shifts, you see that the constant that we're adding or subtracting is on the outside of our exponential function, right? So if you have a function and you're adding a constant, it's going to shift it upwards, right? So if I originally have an exponential function, it's just going to move it up by c units. If I have a minus c, that's going to move it down c units, right? Minus c, like that, right? So that's the simple up, down. Now with the left, right, if you remember from way back, the plus is actually going to shift it to the left, right? Plus c is actually going to go to the left c units, and minus c is actually going to go to the right c units, right? So the horizontal, hopefully you remember, does the opposite of what you think it'll do, of the opposite of the sign that you see, right? So that's how the shifting works, right? Same way that it worked before. All right, now reflections. We haven't done that many reflections, we haven't seen a lot of variety in the reflections. If you see a negative on the outside of your exponential function, right, so right in front of your base, that's going to be a reflection over the x-axis, right? So if I originally have a function that looks like that, remember the x-axis goes like this horizontally, it's going to flip it and it's going to go down like that. All right. Now if I have a reflection about the y-axis, that's when our negative is going to be with the exponent and not the base. So if I had a exponential growth function like this, remember the y-axis is going up and down. So reflecting about this line is going to look something like that. All right. Any vertical stretching or shrinking. A vertical stretch happens when we have a constant in front of our function. It is a stretch if our constant is bigger than 1. It is a shrink if it is between 0 and 1, right? And that we've talked about that before. So basically, if I had an exponential function like this, our stretch, right? So if our stretch is going to pull it up, it's going to make it a little bit longer. It's going to look something maybe like that. And then our shrink, right, is going to smush it down a bit, and it's going to look maybe something like that, for example. All right, and then if I have a horizontal stretch or shrink, this is something that we didn't really talk about, I think, at all when we had originally learned it back in chapter 2.5. A horizontal shrink horizontally shrinks the graph, and you're going to see that a horizontal shrink and a vertical stretch are going to be the same thing, essentially. But if I'm shrinking it horizontally, right, that means this in the horizontal direction is going to get a lot smushed, right? It's going to be something like that. And then if I'm stretching horizontally, right, from left to right, it's going to look a lot longer horizontally than it did before, right? So very similar to vertical stretching or shrinking, there's just little differences between them that are pretty easy to mess up, but we'll do some examples in the remaining slides of this lesson. And again, if you're ever confused with the transformations, make a table, right? Pick a couple values and see what the general shape of it's going to look like, right? As I keep saying throughout this lesson, the shapes of these functions are very predictable, right? You're not going to get any sort of crazy cases where it's going to do some unpredicted shapes and curves and things like that. It's going to be pretty much the same every time, right? You just need a couple points to kind of guide you. All right, so let's look at these first two examples. 3 to the x is something that we've done already. We already know that 3 to the x had a point right here at 0, 1, and 1, 3, right? We've done that before, right? So this is what we originally had. I'll draw it in blue. We originally had something that looked like this. Now the transformation that we have here is a -2. Right, that -2, is it with the exponent or is it on the outside? Right, you see that it's on the outside. It's not up in the exponent with the x, but it's on the outside. So that means this is a vertical shift. And vertical shifts do exactly what we expect them to. If it's a -2, we're going to go down 2. So that means I'm going to take my points and I'm going to shift it 1, 2 units down, 1, 2 units down. Also keep in mind that now the line that we're hugging is not going to be this x-axis. It's going to go 2 units down. So we're going to kind of hug this little line right here. And that's the line that we're going to approach but never touch, right? So it's going to look something like this. So in black is going to be our exponential function for number 9. Again, if you are confused with the transformations, make an f of x table. Again, you don't need that many values, -1, 0, and 1. If you pick -1, you get 3 to the -1 minus 2, which is 1/3 minus 2, right? You're going to have to work it out a little bit, but really we just need a general point to kind of guide us, and that's going to get us -1 and 2/3. Right, so somewhere right there. For 0, 3 to the 0 minus 2 is going to be 1 minus 2, which is -1. 3 to the 1 minus 2 is going to get you a 3 minus 2, which is 1. Right, so that we do get those points right there. And that's enough to graph our exponential function. All right, we could do the same thing with number 10. We have f of x is 3 to the power of x minus 2. Our shift now is going to be in the exponent, right? And in the exponent, we had said that this was a horizontal shift. And horizontal shifts do the opposite of what we think they will. So if you see a -2, it's actually going to go to the right 2. And again, we know that 3 to the power of x is going to look something like this. We've done it before. So in red is our original. And then to graph our transformation, this -2, we're going to shift these points to the right 2 units. And we're going to have a curve that looks something like that. All right, and we can do the same thing here, right? 4 to the x minus 2. I see a transformation, right? The transformation is going to be this -2 that's in the exponent. And we know that that is a horizontal shift. And we're going to go to the right 2 units, right? If we see a -2, that's to the right 2 units. And then 4 to the x, I know that we originally start with 0, 1 and 1, b, which is 1, 4. So we start here, right? Start something like that. Right, something like that. And then our shift is going to be to the right 2 units. So I'm going to go 1, 2 units to the right, 1, 2 units to the right. And then it's going to look something like that. Again, if that confuses you, make a table, pick some points, and see what you get. All right. We can try the same thing with number 12. Right, we have a 4 to the x plus 3, and our plus 3 is now on the outside of our function. I know 4 to the x, we're going to start with a 0, 1, 1, b, in this case 1, 4. So we're going to start here and here. So our original function is going to look something like that. All right, but this plus 3 on the outside, it's not in the exponent. So that means it is a vertical shift. We're going to go up 3 units. All right, so take every point that we just drew, go 1, 2, 3 units up, 1, 2, 3 units up. All right, and then now our asymptote, the line that we approach but never touch, is now 3 units above. It's no longer the x-axis, right? It's going to be 3 units up. So we're going to approach this line but never touch it. All right, so it's going to look something like that in green. All right, so again, more transformations. Number 13, we have a 4 to the -x minus 3. Hopefully we know by now that this -3 on the outside, this is going to go down 3. Right, this is a vertical shift, right, since it is not in the exponent. But we have a -x right here, and that -x is going to be a reflection over the y-axis. Right, so 4 to the x in general, we know that that's going to have 0, 1, 1, 4. So it's going to look something like that originally. Now we have a reflection, right? Reflection over the y-axis. Keep in mind, this is our y-axis, so I'm going to take every point and I'm going to reflect it. So then this point that's right here is now going to go over here, and I know the general shape is now going to look something like that. Right, so that's our reflection, and then bringing it down 3 units, right, I'll do this in blue. I'm going to take every point that's in green right here, and I'm going to go 1, 2, 3 units down, 1, 2, 3 units down, and then we end up with a graph that looks something like that. All right, again, if that confuses you, make a table, right? I'll even make a table right here. We have x, f of x, right? So I'm going to take -1, 0, 1. Right, we have 4 to the -1 minus 3. -1 is a +1, so we get 4 minus 3, which is 1. And then we did, in fact, get that point right there. We get 4 to the 0 minus 3, which is 1 minus 3, which is -2, and we did, in fact, get that point right there. And then we have 4 to the -1 minus 3, which is 1/4 minus 3. That's going to be a little bit less than -3, so we get about -2 3/4. And then that ends up somewhere right there, right? And that's enough information to graph our exponential function, right? You don't need a crazy amount of points. You just need to know what the shape looks like and go from there. All right. This last one here, I don't want to overwhelm you guys with too much information in this first lesson. I know it was kind of long. We see an E here. I'll explain more about E in a later section, but what you guys need to know is that E is a number, right? So if you look in your calculator, right, you can open your phone calculator if you have a calculator, you're going to see a button that says E. E is a number, right? So E, if you type this into your calculator, is going to get you, I'm going to use approximate, is going to get you about 2.718 and so on. Seems like it makes no sense, seems like has no reason to exist. I'll explain more about it in a later section. Hopefully then the existence of this number makes a little bit more sense. But this is just a regular exponential function, right? 2.718 and so on is bigger than 1, so I know it's going to be a growth. This is not a transformation one, by the way. This is just an example of another kind of exponential function. So we're going to do 0, 1, 1, our base E, right? So 1, 2.718, and so on. So I'm going to have a point right there at 0, 1, and then that's going to be a little bit between 2 and 3, and then you can just connect those right there. I'm not sure if in class, I'm recording this before I teach it in class, I'm not sure if I'll go over this at all, but yeah, that's what the graph of that's going to look like. What you guys should at least entertain in the idea of this lesson is just to at least be familiar that E is approximately 2.718, right? It's going to get you a number, right? But again, hopefully this will make more sense in a later section, right? But that concludes this first part of it. The next part of this lesson is going to be solving some exponential equations. But yeah, this first part, we just went really heavy with the graphing. Hope this helps.